Hello and welcome to the last week of new lectures for ECE 108. Since I'm not going to test you directly over this material on an assignment, and since your final is coming up rather soon, the material for this week is on the light side. So in lecture 31, we're first going to examine what the expected value physically really tells us. And this will be followed by examining a few applications of expected value for countable type problems. And then in lecture 32, we're going to introduce the idea of the linearity of an expectation and indicator random variables, along with some application of those topics. So formally, that is not necessarily needed for the final, but it can help you if you know that information. And then we finish lecture 32 up with a comment on the multiplicativity of expected values, or the lack thereof, and kind of hint at some applications of that. And you should note that you will not be tested on the multiplicativity of expected values. That's just some fun information that lets you really see some deeper applications of the material than we really have time to go into. And finally, in lecture 33, I am going to talk about using probability to numerically compute things, such as pi, and how to integrate curves. So again, stuff you won't be tested on, but things that are rather useful in practice, and you have all the material to understand it, so let's just have some fun on the last lecture. Okay, so without further ado, let's get into lecture 31. Okay, so what is expected value really? So previously, we found that the expected value of rolling a d6 was 3.5. Well, there's kind of a problem with that, right? 3.5 isn't an integer, so we can never roll a 3.5 on a d6 because it's not on a d6. So what does this expected value really tell us? Well, let's look at a MATLAB simulation here. Okay, so here I have a script. Let's just go through what it does really briefly. Here I pick a value for n for the amount of d6 I want to roll, and each roll of a d6 would simply be a random number between 1 and 6, so that's what this does explicitly. So rand here, this is generating n random numbers between 0 and 1, and then if I multiply it by 6, and then take the floor of it, that would then be between 0 and 5, and then if I add 1, it's now between 0 and 6. Here I'm kind of computing a thing to hold the average just to speed this process up a little bit. That said, this is not particularly optimized. I just threw it together real quick. Here, so the average for the first roll will simply be what I got on the first roll, and after that, this is just one way I can compute the average relatively quickly without having to recompute data repeatedly. So from here, if I run this with various values of n, it will simulate rolling n d6 and computing the moving average as I go out. So here in this n is equal to 1 setup, the first roll just so happened to be a 3 for here. If I run it again, looks like I got a 3 randomly again. Here I got a 1, etc. I can keep rolling it. There I got a 5, just wherever that dot appeared. So now I can simulate this for, say, 100 rolls. So we know we'll never get a 3.5, but over 100 rolls, let's see what happens. So if I do this, my average, the first one was a 3, the second one was a large number, so I ended up at like 4.5, and then you can see as I go around, this kind of jumps around a bit. So this extra line that you now see is the expected value of what we expect to get if I roll this a lot of times. So now let's just increase this up to 10 to the 6th to see what this looks like. So here you can see as I do a lot of rolls, these blue dots start getting closer and closer to the magenta line. So here if I zoom in a little bit, so if I change my Y limit, so here you can see that it's not exact, but it's getting closer and there's still this little bit of noise. So I can keep running this multiple times, and every time I will get a slightly different result, as you're seeing here. But despite this noise that happens, the average tends to go to the expected value. So this is really physically what an expected value is telling me. If I were to repeat this experiment an infinite number of times and kept doing this averaging process, then in the limit, the average will approach this expected value. So just to do one kind of more zoom in here. So now notice I'm doing 10 to the 7th points instead of 10 to the 6th. So quite a few more points. And here I still get this little bit of variance where it's not exactly going to the mean, but if I keep increasing this, eventually it will converge to that line. That said, just due to the nature of randomness, you'll always have some difference, and there's no really predicting where this will be exactly. Okay, so the run with 10 to the 8 is done. So now if I do that same zoom in, let's see if it looks better. And there we go. So the same range that I had before, and you can see it is kind of getting a little bit closer, but yeah, it'll just kind of always dance around here and eventually will converge as I go off to infinity. So yeah, that's what the expected value is really telling me. So explicitly, the average result approaches the expected value as the number of trials goes to infinity. So this is why this is generally a good metric for things like gambling, etc. You'll see briefly where this metric can break down in some cases. So that said, let's look at a couple of examples. So example 1, suppose that we are sick, and each following day I have a 50% chance to still be sick. So I'm sick one day, and we're just assuming that every single day I flip a coin, and if it's heads, I'm still sick. And now we're going to assume that the probability of being sick on any given day is independent. Okay, and a natural question I can ask is, what is the expected number of days in a row that you will be sick? Well, here, since there is no kind of upper bound for the number of days that I can be sick under this scenario here, we want to know the probability of being sick for exactly for any natural number in days. So what we're going to do is look at the first few natural numbers and find what the probability of being sick is and see if we can find a pattern. Okay, so let's first compute the probability that we're sick for exactly one day. Well, for day 1, we know that we're sick, and there is a 1 minus 50 or 50% likelihood that we are not sick on the next day. So combining these together along with our assumption that things are independent, thus there's a probability of 0.5 that we're sick for exactly one day. So explicitly 1 probability being sick for day 1 times 0.5. Okay? Now let's compute the probability that we're sick for exactly 2 days. Well, for day 2, we're going to need to be sick on days 1 and 2, but not on day 3. So again, we're assuming these are independent events for this problem. So from here, this is simply going to be 1, the probability of being sick on day 1, times 0.5, the probability of being sick on day 2, times 1 minus 0.5, which is the probability of not being sick on day 3. So here, if I combine all these together, I get this 0.5 squared. Okay, so we can continue this process for any arbitrary day n. So on arbitrary day n, there's going to be a 1, the chance of being sick on day 1, times these terms here, the chance of being sick on days 2, 3, 4, all the way up to n minus 1, times 1 minus 0.5. This would be the probability of not being sick on the nth day. So multiplying all these out, I get simply 0.5 to the n. So note that this formula here agrees for n is equal to 1, right? I had a 50% chance the first day. N is equal to 2. I had a 0.5 squared or 25% chance for being sick for exactly 2 days. And yeah, so we have this nice continuity where the same formula works. And again, this is the probability of being sick for exactly n days in a row. So thus from here, we have that the PDF, and here I'm kind of using PDF in quotes at this point technically, is simply going to be this function here. So a natural thing to ask is this really a PDF? So generally speaking, we have a few assumptions that we need for a PDF to be true. 1, all of these probabilities are positive, so that works nice. 2, I want axiom 3 to hold, which we can just assume. And 3, I want it to be the case that when I add up over all of the possible things in my sample space, when I add up those probabilities, I need to get 1, right? Here, our sample space is not finite. It's countable. So how do I really check to make sure that the likelihood of all events is equal to 1? Well, let's do this. Okay, so explicitly, let's check that the probabilities sum to 1. Okay, so since there are a countable number of events, the sum of the probabilities is simply going to be this infinite sum. Okay, so how do we handle infinite sums like this? Well, from Math 119, we know that this is a geometric series, and in particular, it's a geometric series with this value here that's usually denoted by r being less than 1 in absolute value. So this thing will converge. So the next question is, what would this converge to? Well, the convergence formula that you have for a geometric series is only valid when you start at n is equal to 0, and this starts at n is equal to 1. So if I want to use that formula, I need to use the formula and then subtract off the value when n is equal to 0. So explicitly, this would converge to 1 over 1 minus 0.5. All of this, that's the sum from 0 to infinity, minus the 0th term, so 1, or simply 1. So yes, this is a probability distribution function. So yeah, Math 119 and ECE 108 do have these nice connections. Okay, so let's go further. I really wanted to compute what the expected number of days in a row that I was going to be sick was. How do I compute that? Well, let's introduce a random variable. Let d be the random variable for the number of days that we are sick. And now we want to compute the expected value. So the formula for the expected value of d will simply be the sum from d is equal to 1 to infinity. So again, this is the sum over all of the elements in our sample space, and our sample space is the set of all natural numbers. Therefore, I get this infinite sum of d times the probability of d. Well, from the previous slide, we know the probability of d is simply 1/2 to the n, or to the d. So from here, I get this sum. Now, this is exactly a Math 119 type problem to find what this sum converges to. So here I'm going to be a little bit hand-wavy, and in a later example, I'll fill in the details. So first note that the infinite sum converges. That would be a good exercise for Math 119. And the partial sums are given by, so this is kind of a harder exercise, or a standard induction proof, if you get the formula, but the partial sums of this are given by this expression here. So if I add up from d is equal to 1 up to n, this is the expression that I end up getting. Okay, so from here, taking the limit of the partial sums, we have that the infinite sum is simply going to be given by what? Well, the limit as n goes to infinity of this thing approaches 0, so net the limit is 2. Okay, so out of all of this, the expected number of days that we will be sick in a row is simply going to be exactly equal to 2. So yeah, that's a application of what we've been doing in terms of expected value for a problem that is not finite, but still countable. Just as a side note, if you had something that was uncountable, you would want to do the uncountable analog of the sum, which is actually the integral. So if you want to kind of expand from here to go to non-discrete probability, you need to start integrating things instead of doing these sums. Okay, so now to the next problem. Suppose I play a game where I make money based off the result of a fair coin toss. So we've seen a lot of these before, so how is this going to be different? Well, here I'm going to flip the coin until a tails happens, and I'm going to get paid 2 to the number of heads plus $1 at the end of the game. So to be explicit, that is, I get $2 if the first flip is a tails, so 2 to the first. I get $4, so 2 squared, if I get heads followed by a tails, and I'd get $8 for a heads followed by a heads followed by a tails, etc. So the question for this paradox is, how much should you be willing to pay to play this game? So to really quantify this, the go-to method would be to compute what the expected value is. The expected value tells me if I played this game an infinite number of times, how much money would I expect to win, and ideally, if I want to make money off of this game, the amount that I pay should be any value less than the expected value, right? That's what our intuition tells us. So let's kind of compute that and then see why this is a paradox. Okay, so we want to compute the expected value for this game. The likelihood of getting n tails is simply going to be 0.5 to the n plus 1, right? This is the same type of an argument that I applied on the previous page. So the likelihood of getting 0 heads is the likelihood that the first roll is a tails. So that gives me 0.5 to the 1. And the likelihood of, say, getting 1 heads, well, I need to get a heads, followed by a tails, and that'll be 0.5 squared, etc. And the payout for this, well, I was told that's simply 2 to the number of heads plus 1, so simply 2n plus 1. Okay, so from the last example, I know that this likelihood function here is a PDF, so I can just jump through all of those hurdles of potentially checking to make sure it's a PDF and my work is valid, and jump straight to computing the expected value. So how would I compute the expected value of this? Well, I want to take the probability of getting 0 heads and multiply that by the payout. So that'll be 1/2, so the probability of 0 heads, times 2. And then I want to add to this the probability of getting 1 heads and then a tails times its payout. So that'd be 1/4 times 4 and 3 and 4. And I want to keep going, right? So now I can do some algebra to simplify this. 1/2 times 2 is just 1. 1/4 times 4 is just 1. 1/8 times 8 is just 1. If I add all this up, I get infinity. So based off this analysis of the expected value, we should be willing to pay any amount of money to play this game, right? Like, the expected payout is an infinite amount of money. So to see why this is a paradox, let's examine one particular payment. Suppose I pay $1,024 for a single game. What is the likelihood that I lose money? Well, to compute this likelihood that I lose money, I first need to find how many heads do I need to make to break even. Well, to answer that, I need to ask the question, when does the payout equal my input money? So the payout was simply that 2 to the n plus 1. I want to know for what value of n does 2 to the n plus 1 equal 1,024. At that point, I break even. So if I solve that, I have multiple ways of going about this, but the solution is simply n is equal to 9. So that tells me I need to flip exactly 9 heads to break even. So if I flip 9, I break even. If I flip more than 9, I make profit. So the likelihood that I lose money is simply going to be the sum of the probabilities from 1 all the way up to 8. So from here, if I add all of this up, that's a 99.6% chance. So would you play this game? Like, if I only give you one option to play the game, like you get to play it one time, and I'm going to make you pay $1,024 to play this game, would you take this 99.6% chance of losing money in order to play this game that has an expected payout of infinite dollars? Well, most people would say no. And very quickly, if I change that from 1,024 to say 2,048, this probability here very quickly gets larger and larger. So the probability that you get these really large payouts is very, very small. And this is why this is considered a paradox. So it's not a paradox in the sense of like Russell's paradox, where it's a real paradox. It's a paradox in the sense of the birthday paradox, where the conclusion is at odds with what our intuition tells us. So while the expected value for this problem makes you think that you'll be like this, in reality, if you play the game, you're going to be more like this. So this kind of begs a question. What really is going on here on this problem? Well, the probabilities of getting these large payouts is very, very, very tiny. So while in the limit, this expected value goes off to infinity, it's only doing this because I have these really large payouts associated with very, very, very rare events. So for a TLDR, the expected value only tells me the result that I would get on average if I play the game an infinite number of times. But if the expected value is large only due to extremely rare events, then the expected value doesn't really tell me anything about the risk that I'm taking on or the variations in the possible outcomes of the game. So that's another topic altogether that we're not really going to get into. There's the field of decision theory, where you can help to quantize that a bit, and there's the concept of standard deviation in statistics that can also help to quantify it. So let's look at this problem in a bit more detail. So numerically, if I take the average for one experiment, I could get something that looks like this. So here, this is simulating this game, and then over in games, I'm computing the average payout across all of those games. So we can look at this in MATLAB just to generate a few more of these to show you kind of the nature of the randomness. So here, I have a nice first one to play with. So I started with basically nothing of a payout, then all of a sudden I got a really big rare event, and then I kind of get this decay off. Eventually, if I kept playing this, I'd keep getting those rare events pushing the average up. So let's look at a few more examples here. So if I run it again, here I have something more typical, like the one that I had in the figure, where I kind of get these kind of bigger payouts, and these jumps are where I had a really lucky game. And you can kind of tell that it's these rare events that are bumping up the average, whereas most games don't have a big payout. So let's just run a few more things. Like there, I got another good payout. Not as good as the first one. There, I got another good payout. Another good payout. So here, kind of nothing, and then that one there. So you can see just from the nature of randomness, you get these jumps. So really that first one that I got is actually the best one of these plots I found. So I'm kind of glad I got that one on video. So just running one more run. There we go. So here I got some decent payouts at the beginning, and it kind of decayed off here. So yeah, the behavior of these random trials kind of are all over the place, and it just really depends on if you hit these rare events that have a large payout. Whenever you hit one, you get a major spike. And yeah, this is a game where it's not really worth paying much to play it, because as you can see, across this 10 to the 7th number of runs, I'm sitting here at around $40 on average for this trial. And for some of the other trials here after 10 to the 5th, I was sitting down here at 30, whereas sometimes I got that massive value of like 2,000 or whatever it was. So while the expected value does tell you a lot of information, there is this major limitation to expected value on its own, so you should just keep that in mind. Okay, let's look at one more example. So example 2. Recall the example of getting a fair coin flip out of a biased coin. So explicitly, this was the case where I had a coin where the probability of heads was some unknown value, and I wanted to get that fair flip out of it. So in order to get the fair flip, I said I'm going to keep flipping it until I get two results in a row that are different, and then I'll pick either the first one or the second one to be my fair flip. So a natural question you can ask is, how many pairs of flips do we expect to need before we get a heads tails or a tails heads? So in practice, this is really saying, how many times am I going to need to sit here and flip the coin until I can say I have a fair flip? Well, let's tackle this problem. So let P between 0 and 1 be the probability that we get a heads, and let F be the random variable for the number of pairs we need to flip to get a heads tails or a tails heads. So here, my reason for using the number of pairs that I need to flip is more of a convenience factor. It gives me a nice way of actually computing it. And if it turns out that I need 3 pairs, that means I need to do 6 flips. If it turns out that I need to do, say, 0.5 pairs, that means I need to do 1 flip. So we can always turn pairs into individual flips at the end of the problem. So now the thing I need to know here is, what is my sample space for F? If I don't know the sample space, I really can't do anything from there. So how many flips could I potentially need to get a heads tails or a tails heads? Well, it's possible that I could need any arbitrary natural number of pairs of flips, right? It could be the case where it takes 10 million pairs of flips in order to get this heads tails. So here, F is simply going to be some natural number again. So again, I'm dealing with a countable expectation rather than a finite expectation. Okay, so now we want to know what the expected number of flips are. So that's simply the expected value of F. So in order to answer this, I need to know the probability of F being equal to any of these given natural numbers. So the first thing I need to figure out is, what is the probability of getting a heads tails or a tails heads? Well, the probability that we get a heads tails or tails heads on the first flip is simply going to be this probability here. since we're flipping a coin, we're assuming the flips are independent. So this would simply be the probability of tails times the probability of heads, plus, again, since these two events are independent, the probability of tails times the probability of heads. So from here, combining this together and using the fact that I know that this p is the probability that I get heads, this gives me 2 times p times 1 minus p. So again, 2, because I have 2 of these, p, the probability of heads, 1 minus p, the probability of tails. So that's the probability that I need 1 flip. Now I need to know the probability that I need, say, 2 flips or 3 flips or n flips. So now to compute the probability that f would be any natural number greater than or equal to 2, I need to know what the probability that we get the same result on each flip is. So in particular, I need to know what is the probability that I get heads heads or tails tails. And again, we're assuming these are independent events since I'm flipping a coin. Well, this would simply be the probability of heads squared plus the probability of tails squared, and just using the fact that we know that the probability of heads is p, that gives me the p squared, and the probability of tails is 1 minus p, gives me this term here. So now I can put these together like I did in the previous examples to compute the expected value. So the expected value would simply be this, so 1, so that is the value when f is equal to 1, times the probability that f is 1, that's this term here, so 1 times this, plus 2, so 2 is getting 2 flips, so f is equal to 2. Well, in order to get 2 flips, I first need to have a heads heads or a heads tails, so that has this probability here, so that's why that goes here. And then that needs to be followed by getting a tails heads or a heads tails, so it's followed by this probability here. So I need that product. And then for, say, 3, I would want 3 times, well, I need this to happen twice, so that thing quantity squared, again, because they're independent, all multiplied by the probability of getting tails heads or heads tails. And this goes on forever. So cleaning this up a bit, the expected value of f is simply going to be this infinite sum from I is equal to 1 to infinity of this term here. So when I is equal to 1, this thing vanishes, and I recover my first term, check. When I is equal to 2, I get my 2. This thing simply simplifies to this to the first power, check, and I have that term, check. And when I is 3, I match, and it keeps working for the rest of the values. Okay, so from here, I can do some simplifications. So the first simplification is to note that this thing here does not depend on I, right? So since it has no dependence on I can pull it outside of the sum. Now, for the rest of this, instead of doing it all on multiple slides, we are going to jump over to Mr. Paint, and I am going to do it there and just kind of copy-paste style. Okay, so this is what I had at my ending spot here. This is the sum that I want to simplify out. So how do I go about doing this? Well, it can be useful to introduce a new variable that I'll call a, and I will use this from time to time. And a is simply going to be this term here, right? Because this appears multiple times, and it can be kind of convoluted to write this out repeatedly. So I'm just going to call that term a. Okay, so if I call that a, then how can I rewrite this sum? Well, let's just examine this part of the sum here and work on it for a little bit. And then after we kind of notice something about it, we can go back to the full expected value with the term in front. So from here, this, if I use this nomenclature with a is equal to this probability here, well, this whole term here simplifies to a to the I minus 1. So explicitly, this is simply going to be equal to this expression here, right? And equals. Okay, so now that I have this equality here, what can I do? Well, since I have a sum kind of in this form, sometimes it can be useful to write out the sum without using the summation notation. So doing that, I could rewrite this sum as 1 times a to the 0, right? That's what happens when I plug I is equal to 1 in, times 2 times a to the first, times 3a squared, plus 4a cubed, etc. Okay, so how does this help me? Well, it turns out that there's another way that I can rewrite this. Okay, so here is how I'm going to rewrite it. So let's explain where this comes from. Okay, so here you can notice that I have exactly one a to the 0, and I'm going to put that a to the 0 here. Okay, so next I have 2a to the first. So I'll put the first one in this parentheses, and I'll put the second one here, and I'm done with those. And next I have this 3a squared. So here I have my a squared. Here I'll have an a squared, and the term that I did not write here will start with a squared plus a cubed, and it'll keep going, dot, dot, dot. The term after that won't have the a squared in it. And so here you can notice for the 4a cubed, I'll have 1, 2, 3, and the next one would start with a cubed in it. So here, by doing this rearrangement, I'm simply taking these coefficients here and I'm splitting them up into a bunch of sums. So why am I doing this? Well, I'm doing this because it allows me to use things that I know about geometric sums to actually evaluate this sum. So this is a standard trick, and it can be confusing the first time you see it, but let's jump to the next line. So here I can rewrite this whole sum as a double sum, right? So each one of these terms could be rewritten as a sum. So this would say this term here would be the sum from, say, I is equal to 1 to infinity of a to the I minus 1, right? So I start at 0 and go up. This would be another sum, and the only difference, if I leave this as a I minus 1, is that I now start at 2, right? I go from 2 up to infinity. The next one I start at 3 for the bottom index. Okay, so that's a useful property, and if I use that property, I can rewrite this whole thing as this double sum. So what this is saying is the sum from I is equal to 1 to infinity of, add this sum up here where I start at 1, so 1 makes me start at 0 for the exponent, plus then when I go over here to index this to 2, I'm adding up this one, and then when I go to 3, I'm adding up the third, etc. Okay, so how does this really help me? Well, I need to honestly assume a few things about convergence of series that are true in this case. Here I can split this sum into the inner sum and the outer sum. So you can only do that when things converge sufficiently fast. In this case it does, so a little hand wavy on the pure math there. But in this case I can split the double sum into the sum of the outside of the sum of this inside. So now what do I do? Well, this inner sum is simply a geometric series. So from here, from our Math 119 prowess, I can say that this whole term will simply be equal to, well, I'll still have the outside sum just sticking there for the lols. And now the inner sum, I can use formulas that I know. Well, since I'm taking the geometric sum from j is equal to I to infinity, formally this is a Math 119 thing, but I will spell it out here just for completion. You can notice that this sum here is equal to the difference of two infinite sums. So the sum from j is equal to 1 up to infinity of my, that's bad, a to the j minus 1. Now this overcounts some terms, right? Like I don't want all of these terms in my sum. So from here I can subtract from it the finite geometric series, if you will, from j is equal to 1 to I minus 1 of, again, this a to the j minus 1. So if I do this, I can use my formula for these finite sums here and my formula for this full infinite sum, and I can write that this whole quantity is simply going to be equal to this quantity here. Now, in your text, they give another very classic way of deriving this. I just wanted to rely more on the fact that you should have seen this in 119. But if you're not satisfied with that, look on page 93. It's a very standard argument, and if you have questions, feel free to ask me. Now, from here, I can simplify this again by noting that I defined A in terms of P. So if I simplify this out, I can go back to this problem here. So let's do that. So from here, this would simply be equal to, again, the same sum. And instead of this a to the I minus 1, all divided by 1 minus a, I would simply plug in that quantity for a. So TLDR, this whole sum here simplifies via this process to this sum here. So if I put all of this together, I have that the expected value of f is now given by this term here. So now what can I notice? Well, this denominator does not depend on I, right? The only term that depends on I is right here. So I can pull it outside of the infinite sum, assuming everything converges nicely, which it does. So here I can pull that out of the infinite sum and I get this expression here. So now I need to evaluate this sum here. But I've already done that, right? Well, something similar to that. So previously I called this term equal to a, and that's exactly what this expression is. So this whole thing is the same thing as writing this expression here. So as an aside, and let's draw a line. So as an aside, this sum here is equal to this, where a is given by p squared plus 1 minus p squared. And this thing is a geometric sum, right? I know a is going to be less than 1 just by the notion that this is not a certain event. Okay, so now I can use my formula for my geometric series, and I know that this will now simply be equal to, in this case, I'm going to get 1 all divided by 1 minus a. So you might say, why 1 minus a? I'm starting at I is equal to 1, not 0. Well, when I plug I is equal to 1 to here, this thing gives me 0. So essentially, this sum is the same thing as the sum from I is equal to 0 to infinity of a to the I. Therefore, I can use this standard method here without doing anything special. So from here, using the fact that I know what a is equal to, I can rewrite this whole thing as being equal to this expression here. Okay, so from here I have that this is just equal to this expression here, and now I can simplify that sum. So from here I get that this expected value of f will simply be equal to this expression. So all I did was replace this sum with this term here. Okay, so from here I can do some simple algebra. So notice that this term is exactly the same thing as this, so I can combine them pretty straightforwardly as one fraction as this expression here. Okay, now I have this expression. I can do some algebraic simplifications. The book gives some kind of concrete steps that you can take to intuitively simplify it out, but just do the algebra and you get that that thing is equal to this expression here. Okay, so from here we now have simplified the expected value into something that only depends on p and doesn't have any of these infinite sums sitting around it. So just kind of looking at the big picture by zooming out a bit, we started just by kind of intuitively figuring out what these probabilities are to build this expected value. We wrote the expected value as an infinite sum. We noted we can pull some things out to make our lives a little bit easier. We had something of this form, which is a relatively common expression to get when dealing with these type of probabilities. So we applied a standard method of rewriting the sum as a double sum, and assuming nice convergence, which you get given that a is less than 1 in absolute value. From here, I can then split this into an iterated sum, and then just focusing on the inner sum, that's a geometric series, or geometric series with a different bound below. So I know how to simplify that out. And then I can now pull this out of the other sum, and now I still have another geometric series. So bang, using geometric series, I get my solution here. So this is a pretty standard trick to do. And yeah, Math 119 does come in handy. Okay, so let's look back at the lecture slides. Okay, so I kind of went along when I copied and pasted, but here I basically do the exact steps that I spelled out, split this up here, do all this good stuff. So there it is in slide form, and I will stop there for a second. I will save this, and I think I'll make this available as well, just because it's a bit more concise. So you'll get a copy of that when I upload things. Okay, so from here, we can analyze a few cases. So the first thing we can ask is, well, what if the coin was actually fair to start with? Well, if I started out with a fair coin, I would have p is equal to 0.5. If I plug in 0.5 into this expression, I get exactly two pairs of flips. So in this case, 4 flips on average if it was a fair coin. So one thing to note here, in the case where p is equal to 0.5, this expression is exactly the expression that I had in my first example. That's why I did it. So if you look here in the case where p is equal to 0.5, this simplifies to the term here that I had in example 1. So here where I asked us to compute this series here, the technique that I would apply to this is exactly the technique that I'm using for example 2. So that I promised I would show you how to do that. Here's where I showed you how to do it. Okay, so from there we can ask other questions. If it's 1 over 8, then just plug 1/8. I need around 4.57 pairs of flips. So multiply that by 2 for the individual flips. So generally speaking, this isn't a significantly large number, given that the probabilities aren't that horrid. It is a bit more annoying than just flipping it once. And again, note in this 0.5 case, this is the same expression that I had in example 1, and therefore this is the process that shows how to simplify that sum in example 1. A good practice would be to go through and do that manually. Okay, so now we have some assigned reading. I want you to read pages 91 through 93. So the main things to get out of that are basically the examples that I went through, or some of the details if you wanted, like the details for simplifying that algebraic step I skipped over, that's presented in the text. And from here we have a meme. When birds play a game in Petrograd. So Petrograd is an older name for Leningrad or St. Petersburg. So the risk I took was calculated, but man, am I bad at math. Well, yeah, it has an infinite payout, but are you really going to expect to get that infinite payout? Not unless you play a ton of games. And by a ton of games, I mean 10 to the 7th is not enough games to get a good payoff for this run. Sometimes it can be if you're lucky, but yeah, no sane person would pay a lot of money to play that game. Okay, so I will talk to you in the next video lecture, and have a wonderful day.